In this lecture, we will discuss about momentum. Suppose there is a particle in state psi and we want to find the expectation value of x. So this can be done simply by expectation value of x equals integration from minus infinite up to infinite x square modulus dx. But what does exactly this equation mean? Please remember, it doesn't mean that if you measure the position of one particle over and over again, and this term is the average of the results. I mean that the expectation value is not the average of repeated measurements on one and the same system. Because when you do the first measurement, in order to find the position of the particle, simply the first measurement will collapse the wave function to a spike at some value. And if you expect that, the subsequent quick measurements will simply repeat the same result, then it is only possible if you find a way of returning the particle to its original state after each measurement. Because when the wave function is collapsed after the first measurement, how is it possible to bring back the particle to its original position? Hence, this is the wrong way of interpretation of the expectation value of x. Okay, so then what is the right way? So for finding the right way, let's use the concept of ensemble. Okay, in this concept, simply prepare identical systems and each system has a particle in the same state psi and then measure x at the same time. Suppose there is a row of bottles, each containing a particle in state psi, and assign the duty of the student that each student will measure the position of their respective particle at same time. And when once you get the result from the student, simply construct the histogram of the result. That histogram should match with square modulus. And when you compute the average of the result, that would simply agree with the expectation value of x. It means that the expectation value is average of the measurements on an ensemble of identical systems, but it is not the average of repeated measurements on one and the same system. Okay, because expectation value of x changes with time, it is only because of a time dependency of the psi. So when you take the derivative of the expectation value of x, that simply equals integration x derivative of square modulus with time into dx. Now, simply by using the Schrodinger equation, you simply can replace this term by this whole term, where derivative of square modulus with time equals I h cut over 2m partial x into this term. And now by introducing the integration by parts technique, where you have simply u equals x and du equal tx, and you have v equals this term and derivative of v equals this whole term. By introducing the integration by parts, this equation simply equals to I h cut over 2m into this term, where implement the integration limits minus infinite up to plus infinite minus integration of this term, where when x goes to infinite, psi simply goes to 0. So this whole term will become 0. And simply you get expectation value of x equals this whole term, where you have actually two terms, this first term and this second term. Now on the second term, apply again the integration by parts technique. This second term will simply simplify by keeping this 0, and just you will get this term. And this term is similar to this first term, which will add up with this term, and simply you get minus I h cut over m into integration from minus infinite up to infinite psi star partial psi or partial x into dx. Okay, now in quantum mechanics, it is more convenient to deal with momentum, and that momentum equals expectation value of v equals m into expectation value of v. And you know, expectation value of v is nothing but the derivative of the expectation value of x. Hence, expectation value of p equals minus I h cut into this term. Okay, now let me write x and p in a more suggestive way, and that is expectation value of x equals integration psi star x psi dx. You see, I write x in a bold way. Just want to show you that x is acting like a operator now. So this is called position operator, and this position operator tells you that simply multiply this x with the psi. So this is how you will write the expectation value of x. And the way of writing the expectation value of p equals integration psi star into minus I h cut partial x into psi dx, where this is acting like a operator on psi. Hence, x is position operator and this term is a momentum operator. Now, please remember, whenever you apply the operator in in the previous equation, like in this way, just you will sandwich the operator between the psi star and psi. In general, for any dynamical variable, for a particle in a state psi, you simply will write q, expectation value of q equals integration psi star, and you see this operator, any operator term will sandwich between psi star and psi, and you can also write the expectation value of the kinetic energy, which is equal to half mv square, further can be written p square over 2m. Simply now by writing the expectation value of kinetic energy T equals integration psi star into p square over 2m into psi dx. You see, p is the momentum operator. Simply you will take the square of the momentum operator, and that is minus h cut square per second derivative of x into psi dx. And further, simply by simplifying, you get kinetic energy term. Expectation value of the kinetic energy equals minus h cut square over 2m integration psi star second derivative of psi with respect to x dx.